All right, today we are decoding a super powerful technique that's totally changing how we customize artificial intelligence. It's all about how developers can teach these giant AI models new tricks, but way faster and cheaper than ever before. Let's get right into it.
Okay, so let's start with this number. Over 1 trillion. That's how many parameters, or you can think of them as tunable knobs, are inside today's biggest AI models. Every single one of those knobs helps the model remember a tiny little piece of the pattern it learned from, basically the entire internet.
And that sheer scale, well, it creates a massive challenge. I mean, if you want to teach one of these models a new specialized skill, do you really have to go in and tweak every single one of those trillion-plus knobs? It just sounds incredibly wasteful. And spoiler alert, it absolutely is.
So for the longest time, the only way to do it was what's called full fine-tuning. And that means, retraining the whole thing. It takes a staggering amount of computing power. But a much, much smarter approach has come along called parameter efficient fine-tuning, or PEFT. And the whole idea here is to just focus on changing a small, really strategic fraction of the model's parameters.
And that brings us to the star of the show, the most popular PFT technique out there, and the one that's become a huge favorite for developers. It's called LoRA, which stands for Low-Rank Adaptation. Honestly, this is the key that has unlocked efficient AI customization for so many people.
So here's a way to think about it. The original model, with its billions of parameters, that's like a giant printed textbook. It's already published. Now, instead of rewriting the entire book just to add some new info, LoRA is like adding a few small transparent overlays with new notes and diagrams. The original book is totally untouched, but the combined result gives you something new and updated.
The whole idea is just so simple but so powerful. You're not changing the original model at all. You're just adding this small, targeted update right on top of the vast knowledge it already has.
And this right here is exactly why LoRA is so popular. It's just incredibly practical. Because that huge original model stays frozen, a single powerful server can run dozens of different custom versions at the same time, just by swapping out these tiny little LoRA adapters. Plus, the adapters themselves are small, they're easy to share, and they take way less memory to train in the first place.
But all this incredible efficiency leads to a really critical question, one that's been nagging the community for a while. Is this shortcut actually short-changing performance? For years, the common wisdom was that, LoRA is a good enough compromise, but it could never really match the raw power of a full fine-tune.
So, to finally settle this debate once and for all, researchers put LoRA to the test. They ran a whole bunch of rigorous experiments, pitting it directly against full fine-tuning. The goal was simple: find out if this supposed compromise was actually just a myth.
And what they found was, honestly, a revelation. They discovered this clear, 4-part recipe for success that shows LoRA absolutely can match full fine-tuning. It just comes down to getting a few key details right. You got to apply it more broadly than people thought. Make sure it has enough capacity for the task. Crank up the learning rate. And, let it shine in reinforcement learning. Let's break that down.
Okay, first ingredient in the recipe. The old school thinking was to only apply LoRA to a model's attention layers. But what this research shows is that's a huge mistake. The real magic happens when you apply it broadly to all the layers, but especially to the MLP and MOE layers. That's where most of the model's parameters actually are.
And here's the proof in the pudding. Just look at this experiment. That top row, that's the old method, putting LoRA on the attention layers. Now look at the bottom row. That's the new approach on the MLP layers. Here's the crazy part. Even with fewer trainable parameters, the MLP-only approach performed way better. It proves it's not just about how many knobs you tune, but which knobs you tune.
So, once you're applying LoRA to the right places, the next ingredient is the learning rate. Basically, how fast the model learns. And here, the study found this incredibly consistent pattern. As you can see, to perform at its best, LoRA needs a learning rate that's about 10 times higher than what you'd use for a full fine-tune. You gotta let it learn fast.
But maybe the biggest surprise of all came from the experiments with reinforcement learning, or RL. That's the process of teaching an AI through trial and error, like how you train it to play a game or get really good at solving tough math problems. In this area, LoRA doesn't just match full fine-tuning, it crushes it. And the reason, as the research points out, is that this kind of learning gives really simple feedback. Think of it as just a good job or try again signal. And because that feedback is so simple, even a tiny LoRA adapter has more than enough horsepower to learn everything it needs to from it.
So here's the big takeaway.
When you follow this recipe, you apply LoRA broadly, you give it enough capacity, you use the right learning rate, the myth is totally busted. LoRA is not some lesser, compromised version of fine-tuning. It's a true first-class citizen, period.
In fact, it's not just as good, it's actually more efficient. The research shows that for every 3 units of work a full fine-tune needs, LoRA only needs about 2. That's a 33% improvement. You're getting the same top-tier results with way less computational effort.
And this changes everything. It means developers, researchers, hobbyists, anyone can now customize these incredibly powerful AI models faster, cheaper, and without that nagging feeling that they're trading off performance. The paper's title really says it all. This is fine-tuning without regret.
So that leaves us with one last big thought. If the conventional wisdom about a technique this popular was just wrong, what other assumptions are we making in AI right now? What other so-called compromises might actually be hidden superpowers, just waiting for someone to figure out the right recipe?